All right, guys, we're back with another lecture, this time on constant coefficient homogeneous linear differential equation. That is a mouthful. Constant coefficient homogeneous linear differential. I can't believe I took up the whole board. Equations. All right, so that's a lot of descriptors all in one in one phrase. More specifically, we're going to be talking about differential equations of the following form. Let's say we have a sub n times the nth derivative of y plus a sub n minus 1 times the n minus first derivative of y, etc., all the way down to, let's say, a1 y prime plus a naught y is equal to 0. It's got to be equal to 0, of course, because we mentioned homogeneous in the description here. And these coefficients a through a naught through a n, these are just going to be real numbers for us. Okay, so these are just going to be real numbers. Okay, and in point of fact, integers most likely, but real numbers are fine. Yeah, so this is it's somewhat narrow, but we're going to use this as a way to illustrate some of the powers of being able to use linear transformations as a tool. And remember, we're sort of building towards being able to use Laplace transforms. Okay, in the end. So. All right, let's see what we need. To be able to handle this today, again, I always go through the required skills. There's only one required skill today. Okay. Okay, and that is, can you factor polynomials? Yeah, can you factor polynomials? Even larger ones, cubic or quartic polynomials. That don't factor by grouping or anything like that. Okay, so again, if you need to brush up on those things, you can use rational root theorem, synthetic division. You can search for a few ways to do that, but I'm going to go on with the rest of this video, assuming that you can factor any polynomial that I set in front of you that can be factored. Of course, not every polynomial can be factored. Okay, so let's see what we have. I want to introduce first a new notation. Okay. It's not complex or anything like that. It's just going to sort of streamline and simplify some of the things we're going to talk about. So I want to get a concrete example up here. Let's say y double prime minus 3y prime minus 10y equals 0. Okay, so this is constant coefficient. Coefficients are constants. It's a linear differential equation. Again, y prime, y double prime. It's second order. It's going to come up here in a second. And it's homogeneous. It equals 0. So all these things are working for us. Now, what I'm going to do is I'm going to replace the concept of a derivative with a linear operator. I'm going to define a linear operator. I'm going to define d, okay, which will map, let's say, Cn to Cn minus 1. Again, remember what these things are. This is the collection of all functions which have at least n continuous derivatives on some interval I. This is the collection of all functions which have at least n minus 1 derivatives, right? So if I take a derivative of a function that has, let's say, 5 continuous derivatives, if I take a derivative of it, well, the result has at least 4 continuous derivatives. You know, it kind of makes sense. Okay, and so I'm going to define d to be this way, and I'll just define the action of d here, that d of y is just going to be y prime. Again, this is literally representing taking a derivative. Okay, but if I write my notation this way, then I can actually rewrite this equation. Okay, I can rewrite y double prime as d of y. And then I can rewrite y prime as d of y Okay. And again, we understand that this is not multiplication. This is concatenation. It's applying one linear transformation, then subsequently applying the next. Okay, it's a composition of functions, or at least a composition of linear transformations here. But for ease of notation, I'm going to rewrite dd as being d squared. It makes sense. It's a bit of an abusive notation, but you know what? Again, when we understand what we mean when we write these things, as long as everyone's clear on the notation, it's fine. So I'm going to rewrite this, and I'm going to take out my y, right? Because I understand if I apply all of these things to y, then I could just write the entire expression here as d squared, again, 2d's, minus 3d minus 10 applied to y. So again, this it sort of looks like multiplication. Again, it's not. This is a linear transformation which is being applied to y. I could put some more parentheses around y, but again, as long as we understand the notation, it's fine. And what I have here then is, okay, I have now written this differential equation as an expression of a single linear transformation applied to y. Okay, and we refer to transformations of this kind as, so things like this, we refer to these as polynomial differential operators. Okay, polynomial differential operators. It's an operator because it has an effect on something. Specifically, it is a left-hand operator. Our derivative notation only makes sense to the left of an object. I take the derivative of this, so I can't write it. I can't write this as y and then my differential operator. So this is a polynomial differential operator. Okay, and it kind of looks like I should factor this, right? Yeah, we can and we're going to, but I want to cover a few things that are going to make this work. Okay. Now, I've thought about this and I decided the way I want to present this is to actually show you the punchline first and then explain to you why it works. Yes? Okay. So I have this, and what I'm going to do is I'm going to take this polynomial differential operator and I'm going to rewrite this just as a normal polynomial. Now I'm going to replace the d with another variable. I'm going to replace it. Typically we use r. Okay, so I'm going to replace that with an r. This is not strictly necessary. It's just to make it, just to make the writing make a little bit more sense. Because what I'm going to want to do is I'm going to want to solve for the roots of this polynomial. Notice it's the same polynomial. I just replaced d with r. But solving for the roots here doesn't make a whole lot of sense because I can't have something like d equals 7. That's the derivative equals 7. And I don't mean the derivative of a function. I mean the action of taking a derivative equals 7. That doesn't make any sense, right? So I'll replace this. We do have a special name for this. We call this polynomial, which is the exact same one as this. Okay, we call this the auxiliary polynomial. Okay, so this is the auxiliary polynomial. Again, it's the exact same polynomial. I just replaced the d with an r so that I can work with these things in a manner which is a little bit more consistent with the appropriate notation. Now, I'm going to solve for where this is equal to 0. Okay. All right, but that's fairly easy. This factors. I've got r minus 5, r plus 2. It gives me two roots. R is equal to 5, and then r is equal to negative 2. Now, what that tells me, going back over here, is that the following two equations are true. It tells me that, again, using this equation then, it tells me that d minus 5 applied to y equals 0 is true. And it tells me that d plus 2 applied to y equals 0. Now I'm going to work one of these out completely, and then we'll just write down the solution for the other one because it'll be readily apparent. Okay, let's go ahead and apply d minus 5 to y. Okay, the derivative of y, that's y prime minus 5 times y equals 0. This is linear first order, but also separable in whatever way you'd like to solve it. And again, I trust that you guys can solve this. This is going to give me y equals c1 e to the 5, I guess we'll go ahead and use x, okay, e to the 5x, okay. Now, this is telling me that this function here is in the kernel of this linear transformation, right? Okay. Remember, the kernel are all the things that you would apply this transformation to get 0. That's literally what I want to solve for here. So this function is in the kernel of this linear transformation. Now, I ask you a question to think about for a second. Is this in the kernel of this linear transformation? Because this is the solution we're looking for, right? Well, I don't know, okay, but let's keep that in mind, okay? So here we go. Same principle here, gives me y prime plus 2y equals 0. Same scenario. I get y is equal to c2 e to the negative 2x. Fantastic. Okay. Okay, so let's talk about what I've found and whether or not it's useful. I know, because of the proofs we've done previously in class, I know that the solution space to this differential equation is a vector subspace of C2. Okay? I know it's a vector subspace. I also know it's two-dimensional because this is second order. Okay? And what that means is that I don't have to find all of the solutions, right? If the solution space is a two-dimensional subspace, I just need two linearly independent solutions, right? Those two linearly independent solutions will span the entire solution space. And I know that I can just write every solution as a linear combination of those things, okay? The question we have to get into is, well, are these, in fact, solutions to this differential equation? Well, in this particular case, what we can do is we can actually take each of these, plug them in here, and you'll find that these actually are solutions. Okay? Now, we're going to argue why, in a second, we're going to give you an argument for why anything you ever obtain in this particular manner is going to be a solution for your original differential equation, but let me get to that in a second. So, assuming these two are solutions, again, you can just verify that by hand. What I get is that as my general solution, I just get the linear combination of these two solutions. Now, on its surface, this is fantastic because this is a second order differential equation that we were able to solve with nothing more than basic high school algebra. Okay? Well, maybe a little bit here, but close enough. Okay? All right, so let's get to why this works and how, and then I'll cover maybe some slightly more complicated examples. Okay? Okay, so let me erase this. All right. A few questions. When I got down to, maybe leave this. Okay? When I got down to this, it seems reasonable. It seems reasonable for me to write this as d minus 5 d plus 2 y equals 0, or d plus 2 d minus 5 y equals 0. And I know what you might be thinking, well, what's the difference? Well, I changed the order of these linear transformations. And so something you can think about right now, take about 10 seconds to think about it. In general, are linear transformations commutative? If I have two linear transformations, let's say, again, L1, L2. If I apply L1 first, then L2, would I always get the same result as applying L2 first and then L1? Okay. Well, the answer is no. Those things aren't even necessarily well defined. Yeah? I mean, if you consider, let's say, L1 maps R3 to R2, L2 then maps R2 to R1, right? So if I take L2 of L1 of some vector, well, let's see, I put this vector, it must be in R3, my domain. I put it in, the result of L1 of V is going to be some vector in R2, right? Okay, that's fine. So I take, we'll call this V2, and I'll get some value, yeah? But understand, this was a 3-component vector, which got plugged into L1. It spit out a 2-component vector, which I plugged into L2, and that gave me, well, a real number, something from R1. But it wouldn't even make sense to do it the other way, right? If you consider L1 of L2, well, plugging something into L2, I would have to plug in a 2-component vector, and this is going to spit out a real number, because that's what comes out of L2. I don't know how to take L1 of a real number. It doesn't make any sense, right? So in general, you can't swap the order of linear transformations. Not only are they not necessarily commutative, it may not even be well defined for you to do so. But in this particular case, polynomial differential operators are commutative. This is not actually that hard to prove either. Okay? If you consider the fact that if I have, let's say, some polynomial in D, and I have some other polynomial in D, again, these are just arbitrarily long polynomials. This is just a sequence of powers of D with some scalar coefficients, which are being applied to some function y. This would be equal to, again, applying them in the other direction. And the reason for that is, well, all I'm doing is I'm expanding these polynomials and then applying the derivative operator, which is scalar invariant, and the distinct derivative operator that you apply is irrelevant. If I want 2 derivatives of y, it's just taking 2 derivatives. Understand this wouldn't work with partial derivatives, right? Because taking the x derivative, then the y derivative is not necessarily the same as taking a y derivative, then an x derivative. They're typically the same, but they're not the same all the time. So for us, these are fine. And then if I look at this, I have a fantastic way to argue that the 2 solutions I found are not only solutions for these individual factors, but they're solutions for the original equation as well. Remember, for D plus 2, okay, again, when we actually solved that in the lower right-hand corner before now, for D plus 2, we got the solution we got C2e to the negative 2x, right? And so what I know is that this function was in the kernel of D plus 2. Well, yeah, but let's plug it in here. If I plug it in here and I apply D plus 2 to that function, don't I get 0? Isn't that what this says? That I get 0. But doesn't D minus 5 map 0 to 0? If I take this and I plug it in here, D plus 2 applied to this function gives me 0, and then D minus 5 applied to 0 gives me 0. Okay? So what that tells me is that not only is this in the kernel of this expression, this polynomial operator, it's also in the kernel of this polynomial operator. Okay? So while this is a solution for this differential equation, it's also a solution here. Okay, fine. But since they commute, I could have just written it this way, and I can use the exact same logic over here. When we solved when D minus 5 applied to y equals 0, we got y is equal to C1e to the 5x. And again, for the same logical reasons, this function is in the kernel of D minus 5, and then D plus 2 would map the 0 you get, because d minus 5 applied to that function is 0. D plus 2 maps 0 to 0. So again, not only is it in the kernel of this polynomial operator, it's also in the kernel of this one. Well, what this means is that I have found two solutions, 1, 2, to this differential equation. Well, the only thing left to show is, are these two things linearly independent? And they are. In point of fact, it's easy to show, and you should probably try to prove this on your own. It's easy to show that if you have two exponential functions with different exponents, they are linearly independent. So e to the ax and e to the bx are always linearly independent as long as a and b are not equal. Okay? So these two things are now solutions. And so I know I have got two solutions. They're linearly independent, and they're both inside this two-dimensional vector space. I know then that everything in this vector space can be written of the form of a linear combination of these two, which is how we got our general solution. We take the linear combination of each of these two things. Okay? All right, so that's the nuts and bolts for why these things work. Okay? Okay, so where might we run into some trouble? Well, I'm finding roots of a polynomial. So here I had distinct roots. They were real roots, and they both had multiplicity 1. Okay, so two questions arise then. What happens if your roots are, well, not real? What happens if they're complex? And what happens if you have roots that have multiplicity larger than 1? Okay, let me handle the complex roots first, because that's not incredibly complicated, and it uses one of my absolute favorite pieces of mathematics called Euler's formula. Okay, all right, Euler's formula. I'm going to rewrite it. I'm sure all of you know exactly what Euler's formula is, but just for my own peace of mind, I'm going to rewrite this, right? So e to the a plus bi x. Okay. Well, this is a little bit larger than Euler's formula, but I'm writing this because this is what our roots are going to look like. I can rewrite this as e to the ax times e to the bix. Okay. And Euler's formula gives me a way to rewrite this one, the one with the complex exponent. Okay. Euler's formula says e to the bix is cosine bx plus I sine bx. Okay? All right, so again, so this part here, this equivalency is Euler's formula. This is absolutely fantastic. You very much need to remember this. Okay? And again, I wrote this in a somewhat extended version because this is what the roots for our polynomial may look like. They may look like a plus or minus bi. Okay, so, all right, that's a problem. The problem comes in that we're attempting to solve these differential equations over real valued vectors, right? So we want real valued functions, which are solutions to these differential equations. And the problem with this function is that it's not real valued, it's complex valued, okay? Okay, let me work an example real quick to show you how this may come up and what we can do with it. Okay, so all right, let's get a fairly easy one here. Maybe one with, sorry, I'm going to cheat and pull out an easy one that has some complex. Here we go. Y double prime plus 6y prime plus 25y equals 0. All right, this one has complex solutions. Okay, so what do we do? Well, again, the goal here, again, we're going to rewrite this with the polynomial differential operator. Let me write 60 instead. Okay. All right. And again, we're going to look to find solutions to this. It's second order. I know I need two solutions, two linearly independent solutions. But I'm looking to find solutions to this by looking at the auxiliary polynomial. That's just the one where I replace all this stuff with r. I got r squared plus 6r plus 25 equals 0. And again, we can just use the quadratic formula for this. So again, I'm just going to go to my notes here. I assume that you guys can find those. I get, however, -3 plus or minus 4i. Okay, all right, okay. So what does this tell me? Well, it tells me I've got these two. I've got two solutions, right? Remember, I got r equals 5. I got e to the 5t. I got r equals -2. I got e to the -2t. In general, d minus r gives me e to the rt. The problem here is that if I use that same principle, okay, let's call this trial solution 1. Trial solution 1, I get e to the -3 plus 4i. I'm sorry, I said t. We were using x as variables. Okay, and I get, as my second solution, e -3 minus 4i x. And these are not acceptable, right? These aren't acceptable. These are complex valued functions. Now Euler's formula helps me out a little bit, like a small amount. Euler's formula allows me to rewrite these things collectively. Y1 as e to the -3x, and I get cosine 4x plus I sine 4x. Sure. The second one, which I'm going to do a little bit of work to, I get y2 is equal to e to the -3x, again from this one. That's cosine -4x plus I sine -4x. Again, b here is -4. I'm going to make a couple small changes for this. Cosine is an even function. Yes, we remember what even functions mean. So an even function means that f of -x is equal to f of x. And so I can actually rewrite cosine of -4x as just cosine of 4x. Those are equivalent. Okay. Sine's not even, so I can't do the same thing here. But sine is an odd function, right? So sine of -x would be equal to negative sine of x. And so I can rewrite this as minus I sine of 4x. Okay? All right, so I'm going to take these two values here, and I'm going to put a line through this one because we don't want to use that version again. Okay, we want to use these two versions. Okay, now, fine. Okay, but they're still complex valued. Okay, but remember, I know that the solutions I have to this equation are any linear combination of these, right? It's any scalar I can think of times this function plus any scalar I can think of times this function, right? Because again, these are two different values. I know these two things are linearly independent. Okay? Well, maybe if I judiciously pick some scalars, maybe I can take some sum of these two complex valued solutions and come up with a real valued solution. For example, what if I allow the scalar constant for each one of these to be 1/2? Let's see what I get. Okay, so if I take, let me do this in another color. If I take 1/2 times e to the -3x times cosine 4x plus I sine 4x plus 1/2 times e to the -3x times cosine 4x minus I sine 4x. Oh, I need a bigger board. Let's see what I get. Well, what we notice is that I can factor out the 1/2 e to the negative 3x, right? And factor that out from each of these. And now I can just add these together. I see I've got 2 cosines here. So that'll be 2 cosine 4x. But here I've got plus I sine 4x and minus I sine 4x. And plus I sine 4x and minus I sine 4x, those are additive inverses. That's 0. And so when I get, by choosing 1/2 as the scalar multiples to make a linear combination here, this is what I end up getting. And of course, simplifying, the 1/2 times the 2 gives me 1. I just get e to the negative 3x cosine 4x. And this is real valued. Okay? So this is a solution for this particular differential equation. It's a linear combination of these two basis vectors. And it's real valued, right? So let me keep this one. I'm going to write this one down right here. So I'm going to keep this one. I'm going to keep, okay, I'm going to keep, we're going to call this y1 hat. I don't know. I just need to make it different. So y1 hat, we're going to keep e to the negative 3x cosine 4x. Okay, now that worked wonderfully. However, I need a second one, right? I do need a second one. So I got to go back to my basis vectors over here, and this time I need to choose something different, right? So I need to pick something different. I need to pick, let's say, a different scalar, which will give me a different value here. I say, why don't I pick negative 1 over 2, sorry, why don't I pick 1 over 2i, okay? So I'm going to do 1 over 2i times y1 plus negative 1 over 2i times y2. Let's see what comes out there, okay? So that gives me 1 over 2i e to the negative 3x times cosine 4x plus I sine 4x minus 1 over 2i e to the negative x times cosine 4x minus I sine 4x. I can factor out the 1 over 2i and e to the negative x. Gives me 1 over 2i e to the negative 3x. Okay? So now I get cosine 4x minus cosine 4x, but that's 0. And I get I sine 4x minus negative I sine 4x. That's 2i sine 4x. And sure enough, 2i, 1 over 2i gives me e to the negative 3x sine 4x. Now listen, you're not going to have to do this every time. Think about what I just did. Is anything that I just did dependent on the value of a and b here? Well, no. The 3 and the 4 were irrelevant. Okay? Me working this through with the 3 and the 4 was you know, it was just rewriting the same, you know, symbols over and over again, right? In general, and when you won't have to go through this process ever again, but in general, assuming you get the two roots, a plus and minus bi, okay? So assuming you get the two roots to the auxiliary polynomial, if you get r equals a plus or minus bi, these two things correspond to the two solutions c1 e to the ax cosine bx and c2 e to the ax sine bx. This is exactly what we got, right? We got negative 3 plus or minus 4i, negative 3, 4i. Okay. Now, of course, again, these are not my general solution. These are just solutions which happen to be linearly independent. If I want my actual solution, I need the linear combination of these. So c1 times e to the negative 3x cosine 4x plus c2 e to the negative 3x sine 4x. Fantastic. Okay. And again, as long as we're aware of this, there's not a lot of work built into this, right? Okay. So complex solutions, not that bad. We just get some trig functions mixed in. That's not awful. All right, so what about solutions of higher multiplicity? Okay, well, we have to do a little bit of work for that. Not a lot, right? Because again, it's one of those things where like, I'm going to do the work. I'm going to show you how and why it works. And then you're basically going to end up memorizing what the trial solutions are, because working through the proofs every time you need to do this is extremely inefficient. And so I have a couple things that I want to claim here. Okay. The first one is that suppose you have the operator d minus r to some power, some m power, and you are applying this to the function e to the rx times u. U is some function of x. I don't know what the hell it is. I claim this is e to the rx times the nth derivative of u. Okay? We can check this. We can prove it by induction. Okay? Suppose I just take the first one. So let's take d minus r and apply it to e to the rx times u. Well, on the one hand, I have the derivative of this, but that's a product rule, right? Okay, so the derivative of this is e to the rx times u prime plus r e to the rx times u. All right, so this is the derivative of this function. That's a product rule. Minus r times this function. So minus r times e to the rx times u. But notice that these two terms are additive inverses. So I get e to the rx times, isn't that the first derivative of u? That's d u. Okay? So it works, right? And the way inductive proofs work is that now that I've shown it works for the first step, what I do is I assume it works for as many steps up to, let's say, some number k minus 1. And since I know it works there, I can show it works for k. I'll leave the rest of this proof to you. Okay? You can show that this works for any value. Okay? But again, this is now true. Yes? Okay. Finish by induction. Okay. All right, so I need this, and I need one more piece of information here. I need. Okay. I need. Let me separate this off. There we go. Sorry. So I need to know what happens if I have this situation applied to y. So this is one of my polynomial operators, right? And I know that this has roots of higher multiplicity as long as m is greater than 1, right? So again, just as a physical example, if I had d minus 3 to the 4th power y equals 0, so again, same structure. This is a polynomial. This polynomial has the root 3. It just has that root 4 times. Well, this is d minus 3, d minus 3, d minus 3, d minus 3, right? And so, of course, my question then is, okay, so you have those roots, but what are the polynomial roots here? Well, I claim that the following are roots to this polynomial. I claim that e to the rx is a solution here, right? Isn't e to the rx, that's in the kernel of d minus r, right? Yeah, so if I wrote d minus r, however many d minus r's I have, applied to y, this, from what we did originally, This is in the kernel of this first linear transformation, so that'll be 0. And then every transformation applied to that afterwards is going to map 0 to 0. Okay? So that works. But I also claim that x e to the rx is also a solution provided m is 2 or greater. Why? Well, let's see. Why would this be a solution? Okay. So again, let me just write this down. Suppose I have d minus r squared. And let's say I want to apply that to x e to the rx. Okay. Now by this statement here, isn't this equivalent to e to the rx times the second derivative of x? Right? That's what this says, doesn't it? M is 2. You've got r, e to the rx, d2. What's the second derivative of x, though? Well, the first derivative is 1, and the second derivative is 0. This is, well, that's 0 as well. Yeah, so this is in the kernel of d minus r squared. So if you apply d minus r to it twice, you get 0. And then, of course, again, in that giant chain of d minus r's, everything after that maps 0 to 0. The question is, why did this work? Well, this worked because if you have x to the n power, right? You have x to the n power, and you take n plus 1 derivatives of it, okay? Doesn't this always give you 0? Yeah? Again, think about x cubed. Take 4 derivatives of x cubed. X cubed goes to 3x squared. That goes to 6x. That goes to 6. That goes to 0. Okay? Now, that tells me that here, since I know I'm going to be taking at least m derivatives here, that this is true all the way up to x to the m minus 1. Okay? Yeah? All of these things are going to be roots of this, are going to be solutions for this differential equation. Okay? Again, for the same principle we used here. Okay? Now, I mean, that's great, but the question is, did I find all the roots I needed to? Well, let me ask you something. What's the order of this differential equation? Well, the highest power of d, were I to multiply this out, you shouldn't, but the highest multiple, the highest power of d, wouldn't it be d to the m power? Which would imply that it would be of order m, which means I would need m linear independent solutions. If I had m linearly independent solutions, that would form a basis for my solution space, and we can count. X to the first power through x to the m minus 1 power, that's m minus 1 solutions. Add on one more. That's m different solutions. So it turns out this is how we handle roots of multiplicity larger than 1. Again, let me just do a quick example. Let me do a real quick example here. So let's see. Okay. Here we go. So let's say I have d plus 2, d minus 3, third power, y equals 0. I've factored it already for you, wrote it in the polynomial operator notation just to make this a little bit quicker. And so what I have then is I've got the 2 roots here. I've got negative 2, and we got 3, but this one has a higher multiplicity, right? I have this root 3 times. Okay, so again, going back to my trial solutions here, I've got my first one, e to the negative 2x. Again, e to the rx. Here, I've got e to the 3x, but I need 3 solutions. My next one, I'll make x e to the 3x. That's 1, 2. I need one more. The next one I will make x squared e to the 3x. Yes? So again, multiplicity 3, 1, 2, 3 solutions here. They all involve e to the 3x, but they are linearly independent. You can check that, and probably should. Okay. And now let's look at what I have. I've got 1, 2, 3, 4 solutions. And what was the order of this differential equation? Well, this polynomial here has degree 4. This is a fourth order differential equation. I've got 4 linearly independent solutions, which means the general solution then is just the linear combination of all of these. Oh, I forgot the x. There we go. You don't want to forget the x. That's ridiculous. There we go. Fantastic. All right. These are not terrible, right? Yes. A few side notes. So we covered this. So something that does come up every now and then that sort of, I don't know, some students just don't think it through all the way. What if you get the following? What if I got this? What if I got d cubed d plus 1y. Well, let me make this d squared plus 1y equals 0. Okay. Again, we converted it. I'm writing it in the fraction form just to make it easier. Okay, so let's see. My roots would be, well, isn't this just r cubed equals 0? So that's just r equals 0, but it's got a multiplicity of 3, doesn't it? Okay. And this one, d squared plus 1, the roots of that, plus or minus I. Okay. Okay, so how would I handle these things? Well, isn't d minus 0? So r is 0, right? So if I get r equals 0, this should be e to the 0x. Well, yeah, but what's 0 times x? And then what's e to the 0? Isn't this just 1? Yeah? And then again, I've got a higher multiplicity, so my second solution, again, for this particular root should be x e to the 0x. But then similarly, isn't that just x times 1? And then x squared e to the 0x. But that's just 1 times x squared. Yeah. All right, fair enough. These, again, have multiplicity 1. That's a plus bi. A is 0, b is 1. This literally corresponds to cosine x and sine x. Again, e to the 0x cosine 1x, e to the 0x sine 1x. And if I look at a linear combination of these, it's 1, 2, 3, 4, 5 solutions. That's degree 5. I've got y equals, so c1 times 1 plus c2 times x plus c3 times x squared plus c4 times cosine x plus c5 times sine x. This gives me my general solution, but I mean, c1 is a constant times 1 is just c1. Notice that this is how you get polynomials, right? So we have exponential functions, trig functions. This is how we achieve polynomials as part of our solution, right? So polynomials, again, are just 0-powered exponential functions, okay? All right, so this is not a terrible section. It's fine as long as, again, you got to know how to factor polynomials, right? You got to know how to factor polynomials, okay? Yeah, okay. All right, guys, it's my third lecture. Hopefully I'll be able to get all of these uploaded and you guys will be able to be viewing them before I make more. Side note, I mentioned this in the note that I left online. I take suggestions. Be kind. This makes the third lecture I've ever done online. I don't thoroughly enjoy it. It's a little weird for me, but Okay, and I'm a little distracted. I got some ribs cooking right now. I'm very hungry. Anyway, neither here nor there. Okay, but again, if you have questions or concerns or comments or suggestions or even some constructive criticism, again, please feel free to email me. As normal, I will post your homework online, and good luck, guys.